Now we are going to examine the Mandelbrot iterations. We want to show what happens inside the iteration loop. Reminder: the Mandelbrot set consists of all Julia seeds in the complex number plane that produce a connected Julia set. And whether a Julia set is connected or not is determined by checking the zero value of the Julia set. If the zero value escapes, it is not connected. This is the reason why all points of the Mandelbrot method start at point 0. While the image is shrinking, we see the grid with some marked circles. The inner one is a unit circle. The second one is a circle with radius 2. The third circle at 4 marks the bailout cutoff distance. Points leaving this circle are considered never coming back, because 4 squared is already 16 and the point will never be reduced to 0 again. The translation in the first iteration moves the points to their starting locations. This addition stays the same for the rest of the iteration for all points. And now the scaling is visible for the first time. All points are laid out nicely in their starting grid layout. The distance between 0 and each point becomes squared. This leads to this pattern we just observed. Now the rotation becomes visible for the first time. All angles become double. Points on the positive x-axis do not move at all, because the angle is 0. Points on the negative x-axis move by 180 degrees. The translation is even individual for every point. Their starting location is added over and over. The bailout step is performed, which means that points above a certain distance are colored in the current iteration color and move back to their starting locations, forming the image. The complex multiplication consists of a scaling and a rotational part. It does not matter in which order this happens. Either scale, rotate, or rotate first and scale then. The result is the same. We use scale first, rotate then throughout this video. The x-axis represents the real part of the complex number and the y-axis the imaginary part. We will only refer to them as x and y-axis throughout the video. In our visualization, the two-dimensional points move into the third dimension to indicate the overall distance the points move. The larger the distance, the higher the points jump. The scaling is performed by squaring the distance to 0 of the individual points. Points inside the unit circle become dragged to the center. Points outside the unit circle move away from the center. The farther away, the faster the movement in an exponential relation. Here it is nicely visible that points below 1 move towards the center, and points above 1 move farther away. The scaling along the unit circle is exactly 1. Hence, these points on the unit circle do not move. The rotation from a different angle. The translation. Each point is moved individually. by its starting location. The translation from a different angle, isn't it marvelous? The translation from a different angle, I just can't get enough of. Wow. The complex squaring doubles the angles. This has the effect that points on the positive x-axis do not move at all, and points on the negative x-axis rotate by 180 degrees. The bailout distance chosen here is 4. Points leaving this circle never come back, because 4 squared is already 16. And the points will never be reduced to 0 again, since we take starting locations from roughly positive 2 to negative 2 on the x and y axis. The further we continue with the iteration, the fewer points escape. The complex squaring doubles the angles. This has the effect that points on the positive x-axis do not move at all, and points on the negative x-axis rotate by 180 degrees. The scaling. Points with a distance below 1 move to the center. Positive x-axis do not move at all, because the angle is 0. Points on the negative x-axis move by 180 degrees. One of the interesting aspects of the Mandelbrot iteration that becomes visible is a two-step behavior. It seems that one time more points gather in the center, and after that the points become rushed farther away again, which is followed by a gathering around in the center again, over and over. The scaling. Points with exact distance 1 do not move at all. The rotation doubles the angle. The scaling. The distances are squared, leading to exponential growth and shrinking. The points gather around periodic sequences. The negative 1x is such a periodic sequence of length 2. Minus 1 squared becomes 1, but then negative 1 is added and moves it to 0. In the next iteration, 0 times 0 stays 0, but negative 1 is added again, bringing it back to the starting location. So we have a two-step sequence. The scaling. Points with a distance above 1 move farther away from the center. rotation. Points on the positive x-axis do not move at all. They have a polar angle of 0. The rotation. Points on the negative x-axis become rotated by 180 degrees, because their polar angle is 180 degrees. The rotation. Points slightly below the positive x-axis become rotated by around 360 degrees. The rotation. Points on the positive y-axis become rotated by 90 degrees, because the polar angle is 90 degrees. The translation. Points farther away from the 0 move a larger distance. The translation creates such beautiful patterns. Yeah. Let's watch the translation again from a different angle. The translation is just beautiful. It becomes more beautiful in every iteration, especially in the higher iterations. It is fascinating. Isn't the translation producing beautiful patterns? Wow. Wow, wow, wow. When I saw the movement for the first time, I fell from my chair. Really. I love it so much. Those translations. Wow. This is the last iteration. All points that did not bail out until now are considered belonging to the Mandelbrot set. Here we move them to their starting locations and color them black. And this is the resulting image. Thank you for watching and see you next time.